Hello everyone. The title of this video is Identifying Zeros and Their Multiplicities. Alright, so each example I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 5.3, called Graphs of Polynomial Functions, and under the heading Identifying Zeros and Their Multiplicities. And each example I'm doing is going to be either an example taken from this reading or one of the try it problems from the reading or one of the exercises at the end of the section related to this particular objective. Alright, so the first example I want to do is called, the try it problem number 2 from the text. But before I even get into that, I want to talk about zeros and the multiplicity of a zero. Alright, so suppose we're given a polynomial function and you should know what those look like by now. F of x equals, and then some number a sub n times x to the nth plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus a sub 1 times x plus a sub 0, right, where all the a sub 0, a sub 1, a sub n minus 1, a sub n, all these a's are just real number coefficients, and then the variables are all to whole number powers, right? So you're not going to see any negative powers or fraction powers or decimal powers. The powers are going to be 0, 1, 2, 3, 4, 5, 6, 7, and so on. Alright, now we've seen this before in a previous video, but I'll just redefine it here. A zero of the function is an x-intercept, also called a root. But another way to put that, a zero of the function is any value x equals, let's just say r for root, right, root 0, x-intercept, all the same meaning, such that when you plug it in, right, such that f of r equals 0, right? Basically any number that you can plug into the function and get 0 back, right? Thus the name 0 of the function. Alright, now one thing you're going to notice, and this will also come up in a future video, this is a big thing here. If x equals r is a 0 of the function, then the quantity x minus r will be a factor of the polynomial. And that's huge. And it also goes the other way around. We're going to see later that this works in both directions. If you know a factor, say x minus 2 was a factor of a polynomial, then x equals 2 would be a 0 of that polynomial. Right. So now I have a definition of what it means to be a 0. Talking about when you know a 0, you know a factor. And then finally, so I guess I'll put some dots next to this. Finally, the definition of multiplicity of a 0. So if, say, x minus r to the mth power, and where m is some whole number, say this is a factor of the polynomial, but x minus r to the m plus 1 is not a factor. So basically, you have the factor of x minus r m times, right? But not m plus 1 times, right? This is the maximum number of times you're seeing x minus r show up as a factor. Then we say that the 0, x equals r, has a multiplicity of m. Another way to say this, that I'll just say out loud, is the multiplicity of a 0 is just the number of times x minus that 0 is a factor. So some examples of this, and I'll also show you some graphs, right? And then we'll get finally to the try it problem. So some very simple examples. Say f of x was equal to just, 2 times x minus 5, or 2x minus 10 if you distribute the 2. 2x minus 10. This has a 0 of x equals 5, right? Since x minus 5 is a factor, right? Clearly, if you plugged in 5, the output would be 0. And you see the power on that is the first power. The power on that factor is 1. So we would say it has a multiplicity of 1. So it has 0 of x equals 5, right? You plug in 5, you get 0. And the factor x minus 5 shows up 1 time. So they'd say that that particular 0 has a multiplicity of 1. And look at the graph. All right, now the graph of this would just have, 5, 0, and have a slope of 2, right? So the graph looks like this. And look at what happens at that intercept, right? At that x-intercept, at that 0. See how the graph crosses over the x-axis? Alright, the graph crosses over the x-axis at x equals 5. Alright, goes from being negative to positive, or positive to negative for some other cases. Alright. Now another example would be, say, f of x equals 3 times the quantity x minus 2 squared. This function, now you can multiply it out if you want. This would be a 3x squared minus 12x plus 12, right? Because this would be x squared minus 4x plus 4, and then you're distributing the 3. But this has a 0 of x equals 2, right? If you were to plug in 2, clearly the output would be 0. And this 0 of x equals 2 has a multiplicity of 2. Because the factor x minus 2 has a power of 2 on it, right? The factor x minus 2 shows up twice. Now if you were to look at the graph of this, right, it would cross at 2, 0. And this would be a parabola, right? With 2, 0 would actually be the vertex, right? We talked about finding vertex. It would go through 0, 12, and then 4, 12, and it's a parabola opening up. Now do you see what happens here around the graph, what happens to the graph around x equals 2, it hits the x-axis but doesn't cross it. It bounces off, and we'll call this, bounces off the x-axis. All right, so why is that? What's the major difference between these two examples? This first example I showed you, x equals 5, has an odd multiplicity, right? A multiplicity of 1. Whereas in the second example, x equals 2 has an even multiplicity. It has a multiplicity of 2. And this is going to be the case in general. All right. So in general, we're going to see this in all our graphs, and I'll go to the Desmos website a lot and show you. But in general, at a 0, right, at an x-intercept with odd multiplicity, so a multiplicity of 1 or 3 or 5 or 7, right, odd, at a 0 with odd multiplicity, the graph, right, the graph of the function is going to cross over the x-axis. All right, and then add a 0 with even multiplicity. Add a 0 with even multiplicity, it'll be like this parabola here. The graph will hit the x-axis but not cross it. It'll bounce off. All right, so something like this. Or say there's the intercept there, there's the 0. It'll hit it and then bounce back. It'll stay on the same side of the x-axis around that 0. The graph, bounces off, we'll say, the x-axis. And that's really the most important stuff here, all right, we're going to need to know. And one other thing I'll point out is that the higher the multiplicity, the flatter the graph will be near that 0. Maybe I'll put that down here. Higher multiplicity leads to more flatness near the 0. And that's all you're going to really need to know for this particular section of this text. Higher multiplicity leads to, I'll say more flatness near the 0, near the intercept. Okay? Alright, and I'll show you this in the Desmos site. What happens when I increase the multiplicity. You'll see the flatness occurring. Alright. Okay, so finally back to try it problem number 2. Alright, example 1 I want to show you. Try it problem number 2. So you read through here, you got some stuff to read, examples, definitions, all this. There's example 6, and here's try it number 2. It says use the graph of the function, and they're telling you it's degree 9. Alright, so I guess one other thing I should have pointed out is that the sum of all the multiplicities, just to point out up here, if it's a polynomial function of degree n, the sum of the multiplicities should be that, the degree. And we'll see this with plenty of polynomial functions in this video and in future videos as well, that if you take a look at every complex 0, right, not just the real zeros, and add up their multiplicities, the sum of the multiplicities will be the degree of the function. Anyway, back down here. So they're telling us it's a polynomial function of degree 9. Identify the zeros of the function and their multiplicities. I'll draw a rough sketch of this. So here is a very rough sketch of the drawing they had for us. Now, we see that the zeros, and I've already written them out here, but you could see that from the graph. The zeros are at x equals, -5, right, where the graph is on the x-axis. X equals -1, right, there's another x-intercept, and at x equals +3. All right, now let's talk about their multiplicities. And again, you should be able to have a rough idea as to what the multiplicities will be. Right, multiplicities. Now, you see at x equals -5 how the graph crosses over the x-axis, right? So that means it's got to have an odd multiplicity, so either 1 or 3 or 5 and so on. Now, it doesn't cross straight over. Right? You saw my graph earlier of a line. When the multiplicity is 1, the graph crosses straight through, just like a line, like a degree 1 polynomial, right? A linear function. And I mentioned to you, as the multiplicity gets higher, it crosses more flatly. So this looks more like a cubic, right? You see, remember the cubic function looks something like this, right? Y equals x cubed. See how the graph is like a cubic polynomial here at x equals -5, which is a degree 3. So if I had to guess, based on just the look of the graph, I would say that the multiplicity of this 0 of x equals -5 was 3. Right? Just because of how it's crossing the x-axis there. Now if it were even flatter, I might say 5. Right, just based on the flatness, but it looks like it's barely curving, just like the cubic function at x equals -5. So it has a multiplicity of 3. And that would mean that x plus 5, right, x minus -5, x plus 5 would be raised to the third power in the factorization of whatever this polynomial is, but we're not getting there yet. All right, now let's look at x equals -1. Now you see here it bounces off. All right, see the graph touches the x-axis and bounces off, so it's got to have an even multiplicity, so 2, 4, 6, 8, and so on. Now you see here, see how the graph just touches and bounces? It's not really all that flat like it is over at x equals 3. It's really flatter over here. Not very flat. It's like a parabola. All right, this is like a parabola. Right, just coming down and curving up, like in the example I showed earlier. A parabola will just simply touch and bounce off, and it's not very flat at all. Right. So based on that look of the graph at this 0, I'll say the multiplicity is 2. All right, so let's say x equals -1 is a multiplicity of 2. So far that's a multiplicity of 5 total. And they told us this thing was a degree 9. Right, and the sum of all the multiplicities, in these early examples, the sum of all the multiplicities of the real zeros they're showing us should be the degree. Later we'll see that it's the sum of all the multiplicities of all complex zeros, so even ones with imaginaries should add up to the degree. All right, and look at this last 0. So again, the graph comes down, it touches, and then comes right back. It bounces off. All right, so once again, we should have an even multiplicity, 2, 4, 6, 8, or so on. But you notice how it's kind of flatter than a parabola here. See, it's not just coming in, touching, and coming right back. It's coming in very, very, more flatly, if that's a word, right? In a flatter fashion. So I would say it has a higher degree or higher multiplicity than 2, and I'm just going to say 4 because that would add up to 9. Right? We want the multiplicities to add up to the degree. Right? So if you look at all these, right, and again, the sum of the multiplicities should be equal to the degree of the polynomial. Right? And this is for all complex zeros, not just the real zeros, as we'll see later. Okay? But yeah, so again, if it crosses over, that 0 should have an odd multiplicity. 1, 3, 5, 7, blah. If it just bounces off the x-axis, that 0 should have an even multiplicity. And the flatter it comes in, the higher the multiplicity. All right, just keep that in mind. And the sum of the multiplicities of all the complex zeros, not just the real zeros, should be equal to the degree of the polynomial. A lot of stuff to think about. All right, so that was try it number 2. All right. Now I just have some examples right now, and again, they're taken directly from the text. Just you'll have to go searching for them if you want to see exactly where I just wrote them out. All right, so for the rest of my problems, I have them written out, these polynomials, in kind of a factored form already, most of them. And we're just asked to find the zeros and give the multiplicity of each, and then I'll show you the graphs, all right, on the Desmos site. So zeros, I'll make a little chart with their multiplicities. Now, the factors here, x plus 2 is a factor of this polynomial, right? It's a product already, it's in factored form already. That means x equals negative 2 is a 0. Right, because negative 2 makes this factor equal 0. If you were to plug in negative 2, the whole thing would be, you'd get an output of 0. So negative 2 is a 0. And then what's the power on x plus 2? How many factors of x plus 2 are there? There are 3 of them. And that's the multiplicity of that 0. And it's x plus 2 to the third power. And then x minus 3 is a factor, meaning that x equals 3 is a 0. Right? If you were to plug in 3 for x, the output would be 0. And then how many times is x minus 3 a factor? Well, twice, right? It's x minus 3 squared, and that would be the multiplicity of that 0. And so you see, right, the degree of this polynomial would be 5, right? 3 plus 2. And you could, if you were to multiply this out, right, the lead term would be x to the 5th power. And now if you were to graph, right, and the lead term would be x to the 5th. So, positive lead coefficient, odd degree, have to go down to the left, up to the right. We'll talk more about end behavior again in a future video. I mean, I know I've discussed end behavior before as well in a previous section. And then the zeros are at negative 2 and positive 3. Negative 2, you have an odd multiplicity, right? So it's going to come up and cross, but it's not going to cross straight through. Right, that's not a multiplicity of 1, it's a multiplicity of 3. So it's going to come up and cross like a cubic. A little more curvy here, but it'll still cross. Right, just not straight through. Then it's got to turn around at some point and then come down and hit x equals 3. Now x equals 3 has an even multiplicity, right? Multiplicity of 2. So the graph's going to act like a degree 2, like a parabola. Right, so it's just come down and then turn immediately, right, like that. All right, but let me actually show you a much better picture of this. Right, let's punch this into our, there's a free online graphing calculator, right, desmos.com. I know I've shown this in plenty of other videos. We have f of x equals quantity x plus 2 cubed times x minus 3 squared. Right, and do you see it? Right, you see how the graph crosses at negative 2, 0 like a cubic polynomial, not straight through. and then it crosses at x equals 3 just like a parabola. Right? I mean, it bounces off. Sorry, it bounces off like a parabola, do multiplicity 2. And the end behavior is the way I want it, right? Down to the left, and it ends up going up to the right. And remember what I said about the multiplicities, the higher they get, the flatter it will get? Like, what if I increased x plus 2's multiplicity, negative 2's multiplicity to 5? And then 7, and then 9, and then 11. And look at this. Look at how flat it's getting around negative 2 now. See, it's not just coming in like a cubic. It's coming in and then getting very, very flat around the intercept. All right. How about over here? Same thing at x equals 3. Let me go back to the original x plus 2 cubed. All right, you see how it's coming in like a parabola here. Let me change the multiplicity of 3 from 2 to, I'll keep it even. Let's go 4. And you see it's even flatter around x equals 3. How about 6? See, much flatter. Then 8, much flatter. And I'll do one more. Let's go up to 10. You see how very, very, very flat it's coming in. Still bouncing off, right? Still coming in x equals 3 and then bouncing off the axis, not crossing over because we have an even multiplicity, but it's getting much, much flatter near x equals 3. All right, so that's what I was saying earlier about the higher multiplicity, the flatter the graph will be near that 0. Okay, and now my next example, pretty similar, just finding the zeros and stating their multiplicities. I'll show you the graph. So here we have f of x equals x cubed times x minus 1 cubed times x plus 2. Again, it's nice and factored already. So if it's already factored like this, I feel the zeros should be easy to state, and so should their multiplicities. X is a factor, so clearly x equals 0 is a 0. Or if I were to plug in 0 for x, the output would be 0. And then how many times is x a factor? 3 times. Right, so that would be the multiplicity of x equals 0, multiplicity of 3. X minus 1 is a factor. Right, so x equals 1 would be a 0. And how many times is x minus 1 a factor? 3 times. Right, it's x minus 1 to the third. So again, multiplicity is 3. X plus 2 is a factor. So negative 2 would be a 0, right? X equals negative 2. And x plus 2 is a factor 1 time, right? So the multiplicity would be 1. Add them up, this degree, this is a degree 7 polynomial. 3 plus 3 plus 1. In fact, the lead term, and I've mentioned this in previous videos, you just multiply the lead term of every factor, x cubed times x to the third power, right? Again, times x would just be 1x to the 7th. So if I was to make a rough sketch of this, x equals 0, there's an x-intercept, x equals 1, x equals negative 2, and it's an odd degree positively coefficient, so it should be going down to the left and up to the right if you're talking about end behavior. And it's going to come from down to the left, come up, it's going to hit negative 2. Now you see how negative 2 has an odd multiplicity, but it's a multiplicity of 1, so it's just going to cross like a straight line, just straight through. Then it's got to turn around at some point, and it's going to hit x equals 0. Now x equals 0 has an odd multiplicity as well, so it's going to cross over, but it's not going to cross straight through like a line. It's going to cross like a cubic. It'd be a little flatter, like that. And then it's got to turn around at some point to get back to x equals 1. And then x equals 1 also has a multiplicity of 3, so it's going to cross like a cubic again. So like, again, not straight through, but just a little more curvy. So something like this. Now let's take a look. All right, go back to that Desmos site, and I'll enter the function they gave us. Right, we have f of x equals x cubed times x minus 1, also cubed, times x plus 2. Right, and let me actually go back and so we can see everything. And yeah, you see negative 2, 0, there's 0, 0, and then 1, 0. And you see at negative 2, 0, it crosses straight through, right? The multiplicity was 1. At 0, 0, it doesn't cross like straight through. See, it kind of curves a little more like a cubic. Right? It still crosses over though, because it has odd multiplicity. And then same thing happens at x equals 1. See, it's not coming straight like a straight line. It's coming in like a cubic, right? More curved. Right? But it still does cross over, because again, the multiplicity is odd. Right? And then the end behavior matches, right? Down to the left, up to the right, like I said. Great. Again, my hand drawing is not perfect, but it's got a rough idea as to what the thing's going to look like. Okay. Next example. Now this one's not totally factored, but I can factor it completely. This would be 2x plus 1 cubed, and then this 9x squared minus 6x plus 1, that's actually one of them perfect square trinomials. This factors to 3x minus 1 squared. Now if you don't like these lead coefficients in there, right, you don't have to have them. You factor out a 2, but then remember 2 cubed would be 8. So you can pull 8 out of that. That's 2 cubed. And then if I pull a 2 out of this, you'd have x plus a half as the remaining factor. But you still have it to the third power, right? Pardon me. Same thing here. If I don't want that 3 in front of the x, you can pull out a 3, but remember it's 3 squared, so I'm factoring out 9 technically. And then if I pull out the factor of 3, or 3 squared, then you'd have x minus a half, or sorry, x minus 1/3, pulled out 3, but still squared, right? There's still 2 of those. So when I totally factor it so I can easily see the zeros, 9 times 8 is 72, so you have 72 times x plus a half cubed times x minus a third squared. So looking at it this way, you might be able to tell the zeros. You could also probably easily tell me the zeros when I look at it back here. But again, I'll make that little table with zeros and their corresponding multiplicities. Negative half would be a 0. That makes this factor 0, and there are 3 of them. Alright, so it has a multiplicity of 3. X equals positive 1/3 is a 0 as well, right? Plug it in here, you get, it makes this factor 0, and there are 2 of them. Right, so it has a multiplicity of 2. And all told, this would be a degree 5 polynomial function. And in fact, the lead term, right, would be 72x to the 5th. Positive 72 x to the 5th power, right? It's an odd degree, positively coefficient. So once again, if you're talking end behavior, it's going to go down to the left, up to the right, eventually. But you have zeros at negative 1/2 and positive 1/3. All right, now it's going to come up and cross negative 1/2 like a cubic. All right, it's got degree 3, it's got multiplicity 3. It's got to eventually turn around and come back down and hit 1/3. But it's going to hit it like a parabola, right? The multiplicity is 2. It's going to hit at 1/3 and bounce off, and then go up to the right forever. Right? So something like this, at negative 1/2 and positive 1/3. And again, let's see. We have f of x equals. We were given this polynomial. I'll just write it the way they gave it to me. 2x plus 1 to the 3rd power times, and then 9x squared minus 6x plus 1. All right, and look, there's negative 1/2 comma 0. And then the other one's at positive 1/3, but it'll probably put it at 0.333. Right? That's positive 1/3. And you see how it's crossing at negative half? It's crossing like a cubic, right? Crossing over the x-axis. And you see at x equals 1/3, it's like a parabola. It's bouncing off. All right? Multiplicity 3, multiplicity 2. Just like I had. And it's going down to the left, up to the right, just like I said it would for the end behavior. All right, looks good. All right, next example. Same thing, it's kind of factored, but not factored completely. If I were to factor this completely, we'd have x, then this 4x squared minus 12x plus 9. You can pull a, this is one of those perfect square trinomials. This is actually 2x plus 3 squared. All right, 2x, sorry, minus 3. Careful, careful. 2x minus 3 squared. Would be 4x squared minus 12x plus 9. And then this last factor, the quadratic here, x squared plus 8x plus 16. This is another perfect square trinomial. That's x plus 4 squared. Right. And once again, if you don't like the 2 in front of the x here, you can pull a 2 out. Just remember it's 2 squared. Right? So that'd be 4. And then you'd have x minus 3 halves left over, right, if you factor a 2 out of here. But again, don't forget that it's squared, and then you got x plus 4 squared. Right? Alright, so now it's in a nice, easily factored form, a factored form where I can easily identify the zeros and their multiplicities. Okay, and clearly the zeros are, x equals 0. I'm hoping that's clear. Alright, and that's x to the first power, so the multiplicity is 1. Right? Then from the next factor, we see that if x were 3 halves, right, 1.5, you'd get an output of 0. And there are 2 of those, right? So the multiplicity is 2. And the last factor here, x plus 4, if x were negative 4, the output would be 0, so the 0 is x equals negative 4. And again, the multiplicity is 2. And if you were to total all these up, this is a degree 5 polynomial. In fact, the lead term, if you multiply all the lead terms, x times 4x squared times x squared would be 4x to the 5th. So again, we have an odd degree positive lead coefficient. That's not always going to happen. Please understand that, right? So it's going down to the left, up to the right, crosses at 0, crosses at 3 halves, touches at 0, touches at 3 halves, touches at negative 4. Now it's going to come up and it's going to hit negative 4 like a parabola, right? Like a degree 2. It's going to bounce off the x-axis. Then at x equals 0, it's going to cross straight through because of the multiplicity of 1. And then turn, and then at 3 halves, it's going to bounce off again, right? Just like a parabola, and do something like this. Right? The graph's going to be something like this, where it's bouncing off at negative 4 and 3 halves, right? Those have even multiplicities, and it's crossing over because at x equals 0 because of the odd multiplicity, right? And it's crossing straight over like a line because it's multiplicity of 1. All right, so once again, let me enter this. So we have f of x equals x times 4x squared minus 12x plus 9, and then times x squared plus 8x plus 16. All right, and you see, right, zooming out here, there's negative 4. See, and you see how it touches the x-axis at negative 4 like a parabola, right? It's got multiplicity 2. Then at x equals 0, let me just go back to home here. See, at x equals 0, it's crossing straight through. And it looks like it's going up and down. It's not, all right, but it's crossing straight through. All right, and then at x equals 1.5, see, it's like a parabola. All right, it's bouncing off the x-axis. Okay, and the end behavior is the way I want it, right? It's down to the left, up to the right, just like I said. It's a degree 5 with a positive lead coefficient. All right, just got a couple more of these. Alright, so example 6. Now this is not factored, but I can factor it. Alright, you should be able to factor this. These have a common factor of 3 and x squared, right? That's the greatest common factor. I pull that out. Then you'd have x squared plus 2x plus 1. And this factors even further. This is actually one of those perfect square trinomials. We have 3 times x squared, and then this factors to x plus 1 squared. So it's nice and factored now. Zeros and multiplicities should be easily gotten now that I have factored completely. Now x is a factor, so x equals 0 should make this 0, clearly. And x is a factor twice, right? So the multiplicity is 2. So the graph's going to bounce off the x-axis at x equals 0, like a parabola. And then x plus 1 is a factor, right? So negative 1, x equals negative 1 would be a 0. And again, there are 2 of those, right? So multiplicity of 2. This is a degree 4, 2 plus 2. In fact, the lead term would be, oh, it's already there. It's 3x to the 4th, right? So positive lead coefficient, even degree this time. So when we're talking about the end behavior, it's going to be going up on both ends, up to infinity, right? It crosses at 0, touches the x-axis at 0, has an x-intercept at negative 1. And again, it's going to come down here. It's going to touch at negative 1 and bounce off, right? Even degree or even multiplicity. Then it's got to turn at some point. So you get back down to 0, 0 here. But again, the multiplicity at 0 is 2. It's going to bounce off again and then go up forever, and should look something like this. Again, let me just verify that. Back here, just type in the function we were given. F of x equals 3x to the 4th plus 6x to the 3rd plus 3x squared. And you see that, right? You see at negative 1, it's like a parabola, right? Bouncing off the x-axis. Same thing at 0. Right, and going up on both ends, just like I said with the end behavior. Alright, now there's one final example of this. So again, we can factor this a little further. This x cubed minus 4x squared plus 4x, I can pull another x out. So instead of 2x to the 4th, I got 2x to the 5th. And if I factor x out of this, we have x squared minus 4x plus 4. And this factors even further. Right? We have 2 times x to the 5th, and x squared minus 4x plus 4 factors to x minus 2 squared. And that's totally factored. Very easy to identify the zeros and multiplicities here. I'm just going to put mult this time. All right. Now x is a factor, so x equals 0 is a 0. But it's it's a factor 5 times. So a multiplicity of 5. And then x minus 2 is a factor, right? So x equals 2 is a 0, and there are 2 of those, so the multiplicity is 2 as well. Add them up, add up the multiplicities. This is a degree 7 polynomial. You can very easily see the lead term here. Right? The lead term is 2x to the 7th. So again, we have positive lead coefficient, odd degree. So the graph's going to be going down to the left, up to the right, for the end behavior. It's going to be hitting the x-axis at 0 and at 2, right? Those are the roots, the zeros. All right, so it's got to come up toward x equals 0 here, but very flat, right? The multiplicity is 5, so it's going to come in very wide and flat, and then like that maybe, and then it's got to turn around at some point and hit x equals 2, and then it's going to bounce off the x-axis, and then go up. Right? So it's going to be like a parabola at x equals 2, just bouncing off the x-axis. But at x equals 0, it's crossing over, but very flatly, right, because of the high multiplicity. And again, let's verify this. This is a very, very, very rough drawing. Let's look at it in Desmos. F of x equals 2x to the 4th times x to the 3rd power minus 4x squared plus 4x. Right? And you see how at x equals 0, it's crossing over, but very flatly. Right? More like a fifth degree polynomial instead of a cubic. Then at x equals 2, see how it's hitting and bouncing off just like a parabola. And the end behavior is correct as well, down to the left, up to the right. It's a degree 7 with a positively coefficient for the lead term. Okay, and that should be it. Right? That's all I've got for the examples for this video. So I'm hoping that watching me go through these 7 examples here helps you out in some way when you're asked to look at a polynomial, either in factored form or not, right? And if it's not factored, I would suggest factoring it completely. Make it easy to identify the zeros and multiplicities, and once you know the zeros and multiplicities, and the end behavior, which again we'll talk more about in another video as well, you should be able to make a rough sketch of the graph, or at least know how it behaves near the zeros, right? If it's got an odd multiplicity, it's going to cross over. If it's got an even multiplicity, it's going to bounce off, right? And the higher the multiplicity is, the flatter it will be, however you want to define flatter. The flatter it will look near those zeros. All right. Thank you very much for watching.